In this video, we're going to talk a little bit about solid mechanics and the concepts of stress and strain. Let's say that we have some arbitrary shaped object, and we apply some arbitrary forces to this object in such a way that they are in equilibrium. The object is not being accelerated or rotated or anything like that. Then we expect that this object will somehow deform when we apply all of these forces. Now, the forces that we apply create internal forces inside the object and basically set up what is known as a stress field. So the forces that are applied to the object create stress. The way that the object responds to those stresses, the way that it deforms and changes shape, are the way that it strains. So stress is the application of forces to an object, and strain is the deformation of that object. Now, for complicated geometries, of course, it's very difficult to calculate both the stress and the strain. But in this video, we're going to examine one-dimensional objects so that we can show in general how the relationships between stress and strain. So let's imagine that we have a bar that's fixed to a wall on one side, and we'll say that it has some length L, and then let's say that we apply a force to this bar with magnitude F. We expect that after we apply the force that this bar will extend some amount, and we'll call that delta L. Now, it turns out that for most materials under light to moderate loads, that the amount that the rod deforms by, or the amount that it lengthens by, delta L, is proportional to the force that we apply to it. So if we were to draw a graph of this relationship, we would say that delta L, we put delta L on the x-axis and force on the y-axis for historical reasons, and we'd see that for low to moderate forces we end up with a linear relationship between the two. Now let's say that we have a bar that's, I'm going to draw this one in blue, or a different color anyways. How about, blue. That we have a bar that's twice as long as the first one. So now our bar is of length 2L, and we apply the same force to it. Well, if we apply a force to the end of this bar of length 2L, we can think of it as two bars each of length L, and each one of those is going to see a force of F on it, right? Because we're going to pull on this bar with a force of F, which, because it's connected here, is going to pull on this half of the bar with a force of F. So each one of these is going to extend by delta L, and in the end, we will end up extending the bar a total of 2 delta L. This suggests that we can define something that we'll call the strain. We represent it by the small Greek letter epsilon, and we define strain as the change in length of the rod over the original length of the rod. And for a rod of a given cross-section, that strain is proportional to the force that we apply to it. Now let's say that we have a rod of length L, just like we did before, but now we're going to say that this rod is twice as thick as the one before. So we're going to double the area of the previous rod. When we do that, what do we expect is going to happen? Well, we apply our load of F on the end of it, and because each one of these rods is resisting against the force that we apply, it's as if this one is receiving 1/2 F, and this half of the rod is receiving 1/2 F. If this is the case, then we expect each one of these bars is going to extend by 1/2 delta L. So 1/2 the delta L that the one bar before extended when we applied the force to it. So that suggests that we can define the stress as the force that we apply divided by the area over which that force is applied, and it turns out that that is going to be proportional to the strain. So if we double the area, we see that the strain is half of what it was for the original rod. Now the constant of proportionality between the two is known as Young's modulus, and we write that as a capital E. So the relationship ends up being stress is equal to E, the Young's modulus, or the modulus of elasticity it's often called, times the strain. The units on these are force per area. The units on strain are length over length, so it has units of 1, which means that the modulus of elasticity, or the Young's modulus, has units of force per area. Steel, for example, has a modulus of elasticity that's usually given as around 200 gigapascals. Now, we can graph the relationship in the end, where we put strain on the x-axis and stress on the y-axis. And again, for low to moderate stresses, for low to moderate forces that we put on this, the slope of this line is essentially constant, and of course it's given by the modulus of elasticity. And then eventually we'll reach a point where it's no longer a linear relationship between the two. And for example, we'll end up getting to a point where we actually stretch the material a little bit. And when we release the material, it may not actually go back to 0 anymore. It may now come back down to some small strain that's basically a permanent deformation. And we define the stress where this starts to occur. We call that the yield stress. So if we go above the yield stress, then our material is not going to return back down to where we started. And there's all kinds of patterns that can happen up here, but as we continue to stress the item, eventually we'll get to the point where it just breaks. So as an engineer, when you're designing something, there are several things you have to take into account, and that includes what the modulus of elasticity is, because you need to know how whatever you're designing is going to bend or deform or change shape under loads. You need to know the yield stress so that you make sure that you don't stress it to a point where it becomes permanently deformed. And of course you need to know the breaking stress, because ultimately you want to make sure that whatever you're designing doesn't break. And that, in a nutshell, is the relationship between stress and strain.